Well, welcome to the second lecture of our class. Before I begin the lecture, I have a few organizational logistics issues. Now, the first homework is due on Thursday, on the Thursday's lecture. Now, Angelica or Daniel are going to collect the homework, then they're going to grade them, and then they're going to return them to you. The same applies to the distance education students. In this case, they're going to use fax. Now, some of these homeworks can look fairly easy. Some can look more difficult. If you have problems, of course, you're welcome to drop by at the office hours. My office hours are Tuesday and Thursday before the classes. Daniel also has office hours at the same time, so if you don't find me eventually, or if you have some simple question, you can also find Daniel. Angelica will have office hours on Mondays and Wednesdays, so if you would like to get some feedback a day before the lecture, you can check for Angelica. If you would like to get some feedback on the day of the lecture, you can look for Daniel or for me. Now, when it comes to these homeworks, you should pay particular attention to dimensions. You have two types of units, SI and CGS. Now, CGS may be convenient in sometimes. In many books, actually, people use CGS system rather than the SI system. You can understand that when it comes to colloidal world, kind of the smaller the base unit, the better, and CGS has natural units which are closer to the colloids. So you can pick one of those units, but make sure that you don't kind of mix them up, because this is the most common source of errors in homeworks. Now, the second homework is available for download. I haven't been thinking too much about how to grade the homeworks. Now I have decided to make the following scheme today. I'm going to assign points to each homework problem, either 5 or 10 depending on the complexity. And then, so depending on how well you did on the problem, you're going to get either the 5 or the 10 points for each problem. So if you have larger homeworks, this means that you're going to have also larger number of points. Instead of trying to make all homeworks to have the same weight, I have assigned weight to the different problems. Now, discussion topics are already available on the web page. What I'll ask you to do is take a look, think about your scientific interest, research interest, and try to pick up one topic by next Thursday. This is January 23rd. Let me know which is the topic. Actually, maybe again the TAs are going to collect the choice of topics. Eventually, if we get more than 2 people who try to sign up for the same topic, one of them will probably have to pick something else. It's on a first come, first serve basis. That's how it's going to work. You have a choice of 5 different general areas during the semester, and I'm going to give you the opportunity to speak at that time when you select, and you're going to, as we discussed, continue the topic which you selected as a short-term paper. The links to the papers are already available, to the downloadable papers are already available on the website. I'm going to, again, by next Thursday, I'm going to organize them in topics. So you can search for the specific topic which you're interested in, and you can find some papers which would give you good starting basis. And then start from there on, find a few more papers in the literature, prepare a few slides or a few PowerPoint slides, and present this when discussion topics are due. So this is about the logistics. Any questions about this? Yes.
The audit students, do they do the class discussion?
You don't have to participate in the class. You don't have to prepare for the class discussions. Of course, you're very welcome to participate, as always. Now, if you would like to prepare for one topic, however, you're welcome. I mean, I would welcome that, and it depends on your interest, but you're not obliged by default. Again, for the auditing students, I would ask the auditing students to solve at least or work on at least half of the homework problems. For the distance education students, we cannot include them in the discussions directly, but they can follow the discussions and then they can prepare the topic which they are interested in for the final short-term paper. Okay, let's get on with the lecture. I know that most of you are interested in this class because of the newer elements which are going to discuss related to nanoscience engineering. However, we have to go through the fundamentals. And in this lecture, what I'm going to do is I'm going to go through the thermodynamics of interfaces. Define surface tension, interfacial tension, adhesion, all those properties that we're going to need from here on. Now, in each of the lectures, what I'm going to do is the first slide. This is obviously not that informative, but there is something that's informative for you here. And this is which are the relevant chapters from the books. Also, when it comes to homeworks, you're going to have in your homeworks, you're going to get the homeworks assigned by book. So you can see that I have given you some problems from one of the books, some problems from the other books, and some additional problems on my own when it comes to the homework. So this is the chapters that you would like to read if you want to get your basics from the book. Now I'm going to go a little bit above and beyond what's in the books, and I'm going to skip some of the sections which I don't find that important. In principle, if you follow the lectures, you should be able to get an idea of this material. Of course, reading the textbooks is always recommended. And again, if you have questions, the teaching assistants and myself would be there to help you during the office hours. Now, somehow I started with a beautiful picture the last time, and this is very similar to the previous picture. So again, we have a soap film. However, here we have two bubbles. Now, why are those bubbles spherical? So why do we have this curved interface here? And then why in the middle between the bubbles you have this straight interface? And if you think about that, why the bubbles are in this specific configuration? Why, for example, they didn't form something like that? What makes them adopt exactly this specific configuration? Obviously, some of you know at least intuitively the answer. And this is that the bubbles adopt this configuration because there is surface tension, interfacial tension, which pulls the film around the bubbles to its smallest surface area. This is what we're going to speak about in this lecture. I cannot give you all the mathematical instruments that are required to calculate surface of complex colloidal objects like that, but certainly at least you're going to know the basics and why this happens from thermodynamic point. Now there is this simple experiment which you may have studied from even from your high school times. Now you take a frame open from one side, you put in some liquid inside, and usually you want to add some soap to this liquid just to keep the film stable. The soap, however, is not that important from the viewpoint of thermodynamics here. And then you can have this movable frame on the bottom, movable part of the frame. Now, if you make this experiment with real film, you're going to find out that the film wants to contract itself. So if you want to keep it in its original size, or if you want to expand the size, you need to pull down on the frame here. Now, if you're pulling in this direction, this means that there is something pulling in the other direction, and this something is the interfacial tension. Now, when it comes to definition, I'm going to use both interfacial and surface tension. Now, surface tension is usually used in cases where we have something in contact with air. Obviously, interfacial tension is the more general term, which applies to surface that separates two phases independent of the type of the phases. Surface tension is also often used in case of solid materials. And we're going to go to the case of solid materials a bit later in the lecture. Now, these simple experiments allow us to define interfacial tension in a very simple way. Now, if there is a force pulling in the other direction, then you can make the mechanical balance if your frame is in equilibrium. So what pulls it up? The force which you apply downwards would be equilibrated by, first of all, the interfacial tension, which I have denoted as gamma. Then you have the distance of the lower part of the frame here, and now you have this parameter 2 here, because if you have a soap film, you have two interfaces. So you have two interfaces pulling this frame upwards over the distance of L. So you can say that kind of this is one definition of surface of interfacial or surface tension. Now you know that thermodynamics usually is not very happy with forces. It wants to think in terms of work or energy. And if you start from this simple definition, you can also think what would be the work performed in order to create some area. So if you want to stretch the film, you have to perform work. Now the work, as you remember from physics, is equal to 4 to the force times the distance. We already have the force for the force sphere, 2 times the length times the interfacial tension. So if we pull it for some distance, and we do this in differentials, just kind of the way it's usually done in thermodynamics, in order to perform a little bit of work, you need to pull the frame a little bit downwards. This multiplied by the force gives you the work that you have performed in pulling the frame. Then you substitute for the energy 2 times L gamma multiplied by dx. And what you're going to notice is that eventually 2 times type L times dx is equal to the surface which you create when you pull the frame. So your surface is this one here. You have to multiply it by 2 because you have film with 2 surfaces. So you end up with a formula which tells you that the work that you have performed is equal to the interfacial tension times the surface that you have created. Now once you know the work, you know all other thermodynamic functions. Now the function that we use usually in colloidal science is the Gibbs free energy. Because usually in a laboratory you work at constant pressure and constant temperature. So we use the Gibbs free energy, which is equal to the volume times the differential of the pressure minus the entropy times the differential of temperature plus the work that we have performed. So we substitute the work from the previous slide here, and we end up with this very basic definition of Gibbs free energy, which includes a term for the surface energy which we have created by moving the frame, which is the term which includes the surface tension, the interfacial tension. Now, let's say like that kind of, I'd like to give you a few questions during the lecture just to kind of keep you a little bit more, keep this a little bit more interactive. Now, if you compare these two terms, this one and that one, do you see any similarity between these two terms? Kind of, can you think of something which relates them? Well, okay, let me tell you like that. Now you have volume and pressure in 3 dimensions. What you have here is tension and surface in 2 dimensions. But in the sense, they are equivalent in the sense that in both cases you have either volume times pressure, and in this case you have surface area times tension. So essentially this is in a way the 2-dimensional representation of this term. So kind of in a way this is the thermodynamic term which takes into account what happens when you create surface and so on. Very much similar to the way what happens when we create volume and move, let's say, a piston, again a 3-dimensional volume. So we can spend energy in 3 dimensions by, let's say, changing the pressure or the volume inside the system. Or we can make energy in 2 dimensions by stretching an interface. Yes, Arti?
I feel like that gamma dA would be more related to PdV instead of VdP.
Right, you're right. I mean, actually, if we have to take the exact equivalent, this should be P times the differential of the volume. Just it happens that we use Gibbs energy, which is the other way. And again, thinking in terms of thermodynamics, you have intensive parameter and extensive parameter. The extensive parameter is the volume or the area. The intensive parameters is the interfacial tension or the pressure. Daniel had a question there.
Well, so if you started with internal energy, then you would see exactly what you're talking about.
Right.
Or what Arthi is.
In a way, where I'm going, I mean, this kind of, where I'm going is like that. Now, let's say we keep the pressure and the temperature constant. So what's going to happen in this case is we're going to have the Gibbs free energy being dependent only on the interfacial tension and area. And formally, of course, we can write this equilibrium here, and then this is a very important definition again of the interfacial tension. We can define the interfacial tension through a thermodynamic function, the Gibbs free energy. So the interfacial tension is the derivative of the Gibbs free energy with respect to the surface at constant temperature and pressure. And now if we go back to the mechanical definition, now this is important and this is the practical side which you need to remember from this part of the lecture. You can have two definitions for surface tension. Mechanical definition, which is the force per unit length, or the thermodynamic definition, which is the energy per unit area. So you can define it like that, or you can define it like this. Now you can say, well, I mean, kind of how comes we have energy and force? Are they dimensionally the same? So you can perform a dimensional analysis. The force per unit length is newtons per meter. Now the energy per unit area is joules per meter squared. Joules, however, is newtons times meter. So you're going to have the meters cancelling here. And you're going to have again the same dimension. So that's why when you let's say you measure interfacial tension. I mean, in the next class we're going to discuss how you measure actually the interfacial tension and so on. When you measure interfacial tension, you have four options of how you're going to write down your results. You can write it in terms of force per unit length, or you can write them in terms of energy per unit area. Or, of course, you can use CGS or SI. So, kind of, I mean, like you can find actually interfacial tension being expressed in any of those four ways. And just to be closer to reality here, I have listed 4 liquids, typical liquids, with their interfacial tension. Now, all those interfacial tensions are in one kind of, all those 4 dimensions are the same. Luckily, when we work in SI, we can use millinewtons per meter, which is equal to dynes per centimeter. You can see why I was telling you that the system CGS is better for studying colloidal science. You can see that in CGS the typical values of the interfacial tension are equal to two of the basic units of CGS. However, if we work in millinewtons per meter, again we have a set of numbers which are between 0 and 100, with some exceptions. So it's kind of a really good number. We don't have exponents, and you can immediately see what is what here and so on. Let me go one slide further, and I'm going to come back, and I'll be happy to answer some questions if you have any. Now, so far we have discussed, I mean, what is the definition of interfacial tension? We have not discussed what is the origin of the interfacial tension. Now, molecularly, this is a big problem. I don't want you to really go into statistical thermodynamics and complex molecular calculations in this class. I just want to give you the idea here of why do we have interfacial tension from molecular viewpoint. What is the reason that the liquids would like to minimize their surface area? Now, this is kind of statistical thermodynamics by rule of thumb. What you could do is, now imagine that this is the interface between two liquids. This interface is never going to be very sharp, by the way. So when we define interfacial tension, we ascribe it to some specific boundary, let's say which is going to be here. But in the reality, you're going to have a little bit more kind of gradual transition. Now, this model is going to work fine for us. Now, we take a molecule on the surface, this one, and we take a molecule in the bulk of the liquid. Now, the energy of that molecule would be equal to 1/2 times the number of surrounding molecules times the pair interaction energy between each two molecules, as a function, of course, of the distance between the molecule and the first sphere of surrounding molecules. Now, if you draw the first sphere of surrounding molecules, you're going to find out that, of course, there are molecules all around the molecule in the bulk of the liquid. Now, the molecules in the liquid will do what? Are they going to attract each other or repel each other? At equilibrium. What would be the condition at equilibrium? Are the interactions going to be more attractive or repulsive? Right. I hear attractive here. Obviously, if they were repulsive, the liquid is not going to be a liquid, right? It's going to evaporate. So the interactions are always attractive, which means that the molecules have a negative energy, so they would like to be inside the liquid. Now, what's going to happen if we consider a molecule on the surface? The molecule on the surface is going to have, first of all, it's going to have a smaller number of surrounding molecules. Roughly, we can say that the number of surrounding molecules is going to be about half of the number of the molecules which are going to surround it in the bulk. In addition to that, the distance between the first sphere, because the surface is a little bit less dense than the bulk, the distance is going to be a little bit higher. All this tells you that a molecule on the surface is going to have less attractive interactions with all the surrounding molecules than a molecule in the bulk. This comes to tell that eventually a molecule would really always would like to be in the bulk energetically rather than on the surface. So when you move a molecule from the surface to the bulk, you gain energy and vice versa. If you want to move a molecule from the bulk to the surface, you have to do energy. You have to spend some work. And this is actually the work which you do when you stretch a surface. This is the work for stretching a surface against the interfacial tension, which also tells us I want to go one slide back here, which also tells us that gamma is always going to be positive. The interfacial tension is going to be positive. Negative interfacial tension would mean a liquid which would like to explode, which doesn't want to hold together and would like to maximize its surface area. You can have a case like that, but this is not the case at equilibrium. So for all practical purposes, the interfacial tension is somewhere between 0 and 100, with the exception of some specific liquids like mercury, which can have very high interfacial tension. Metals. I have a favorite story about making novel materials, but I mean, let's leave it for the case of the novel materials. The poor guys who wanted to infuse a porous material with mercury or liquid metal would have to do lots of work because of the high interfacial area. We'll discuss this a bit later. Now, can you make the interfacial tension smaller? I guess you know the answer. If you add soap, if you add surfactant, it's going to go down. Now, just one general, and the people who have listened to my thermodynamics course should know that. Now, one general kind of relation between the interfacial tension and what parameter of the liquids kind of comes to mind?
Pressure.
Well, what is the pressure of the liquid? Now, when you have a liquid, how do you define its properties?
Density.
Uh-huh.
Density.
Yeah, density will be one. Density will be one. Why? And if you think about density, you're going to immediately see that the density increases in this direction. Now, why would denser liquids have higher interfacial tension? What makes the denser liquids dense?
More molecules per volume.
Right. Why more molecules would like to stick in the same volume?
More attractive.
Right. So you can see the relation. More attractive interaction, more dense liquids, higher interfacial tension. Another parameter which can be related to the interfacial tension is, in general, is the boiling point, which again relates to how easily the molecules would like to leave the surface of the liquid. Okay, so we are done with the definition of the interfacial tension. Now, what are the consequences? Well, the first consequence, of course, is that the liquids would like to minimize their surface area. So when you make a bubble, this bubble does not stay in any shape. It gets to be spherical just because it minimizes its surface area. In the same way, if you have two bubbles, these two bubbles are going to try to minimize their surface area by adopting this configuration, which is the configuration with minimal surface area per the same volume of liquid. So that's why they get to be exactly this conformation. There is a branch of scientists, actually, mathematicians mostly, who do all types of calculations, minimization of area, and all of them illustrate their results with different types of bubbles and soap films and so on. And something that you know from childhood is that if you want to make a bubble, you have to apply pressure. You have to kind of blow, so the bubble expands. If you just leave it open, it's going to contract, right? So what we want to do now is we want to understand what is the pressure inside different colloidal systems, which is caused by the interfacial tension. This looks like lots of equations, but in fact it's very simple. Now we want to calculate what is the pressure inside a small droplet or bubble. The first analogy that comes to mind is you have a, let's say, rubber balloon which wants to contract. Obviously there is going to be some pressure because the surface wants to contract. Now we can calculate the pressure in a very simple way. If we want to keep it at the same volume, or if we want to expand it, we have to eventually do some work for expansion, which is a volume work, purely thermodynamical. We have the difference in the pressure times the volume. Now this work is going to go where? It's going to go for the expansion of the surface of the droplet or the bubble. So we are converting the volume work into surface work. Now we take an expanding bubble here, and let's say its original radius is r. Its radius after expansion is r plus dr. And then we can substitute inside this formula just to obtain the changes in volume and the changes in area, which we need here for these two expressions. Now this is very simple. This is the surface, this is the volume of a bubble after the expansion minus the one before the expansion. So if we change the radius of a droplet or bubble with dr, this is how we calculate the change in the volume. If we change the area, this is what is going to be the change of the area in terms of dr. Then we substitute dV and dA here in these two, and they have to be equal. The equality of the works means that we're going to have this expression. the difference in the pressure times the change in the volume when we expanded the bubble is going to be equal to interfacial tension times the change in the area due to the bubble expansion. And you can see that lots of things are going to cancel here. The dRs, the r squared with r here, the pi's. So if we just rearrange the terms, we're going to arrive at this very simple formula, which tells you that the pressure inside the bubble or the droplet is equal to 2 times the interfacial tension divided by the radius of the droplet. Now, the smaller the droplet, the higher the pressure. This is somewhat anti-intuitive at first until you realize that this is very important. So, the smaller the droplet, the higher the pressure. What I have done here is I have done some calculation actually for, we're interested in the nano region, so for a nanometer size water droplet. If we take a water droplet of radius 10 nanometer, 20 nanometer in diameter, take the typical interfacial tension of water, we do the calculation here, and we end up with a pressure of 140 atmospheres. So this is a very strong effect. I mean, 140 atmospheres is a lot. So this small droplet is going to have enormous internal pressure, and this has lots of consequences in terms of, as we're going to see just in a second, in terms of thermodynamics and in terms of many systems, biological systems, colloidal systems, and so on. All of them, when you have these small droplets, bubbles, and so on, under high pressure, and that is thermodynamically not very favorable. Now, this is an equation which describes only spherical droplets. Now, we know that not everything in the world is spherical, so what is the case if you have a non-spherical surface? Now, any surface can be described by 2 radii of curvature. So the generalized form of the equation is that the difference in the pressure is equal to the interfacial tension times the inverse radii of curvature. For the case of droplets, these 2 radii are the same. So eventually that's why we have this factor 2 here. And kind of, I know that's a little bit difficult to imagine. So I have a question on the next transparency, but before that, imagine that you have a surface which is not exactly spherical. That's I want to illustrate how these 2 radii of curvature work. So one of the radii of the curvature would be the radius which acts in this direction. The other radius would be the perpendicular one, which is in this direction. So this is not a spherical surface. You have 2 radius. One is this one, and the other one is this one. This is the mathematical way to describe complex surfaces. Now, we're going to stop here, take questions, and while I hope you have some questions now. While you're asking questions, also think about this question which I have for you here. Can there be a curved liquid interface without capillary pressure? Now, before you tell me your suggestion, Brian, now does anybody has any question about this mathematical procedure for calculating the pressure inside the droplets and so on?
So the larger the droplet or bubble, the smaller the difference between outside pressure and the inside pressure?
Right. If you expand this to the ultimate case where you have an infinitely large bubble, you are getting to have a flat surface. And the flat surface has no capillary pressure because it's flat, right? There is no pressure operating across an ideally flat surface. Now, the moment you start curving the surface, however, you're immediately creating a pressure because the surface would like to contract, kind of straighten out. Which tells you that the pressure inside large bubbles is going to be smaller than the pressure inside small bubbles or droplets. Now, I'm saying bubbles or droplets, and this is really the case because you don't care really whether you have a bubble or droplet. You have exactly the same, as long as you have the same interfacial tension. it always wants to contract and it always has the internal pressure in the same way. So far we know how the pressure works. We know that once you curve the surface, you have the origin of the capillary pressure. Now, can you have a curved surface which does not have a pressure, capillary pressure across the surface? Can you think of a case like that? Okay, I mean that's good. So Brian suggested saddle point here, and actually it's easy to make such a surface if you take two cylinders or two tubes, and if you put some liquid or some free film between them, you're going to have this type of interface. This, in general, all those curved interfaces are called, a single one would be a meniscus. The plural of that would be menisci. But every time you hear about a meniscus, you can think of some curved interface with liquid inside. Now the point, however, is that if you have a surface like that, the principal radii of curvature pose each other. So the first principal radius of curvature is in this direction, like this, and the second one is in this direction across the... So if you are here, for example, you have one of the curvature acting in one direction, the other acting in the other direction, so they cancel each other. So this is a curved interface without any pressure across the interface. And why the system would adopt exactly this interface, except instead, for example, of straightening out? If you calculate, actually you're going to see that the system minimizes its area by adopting this specific configuration. So again, many people are just doing their daily work by calculating similar interfaces mathematically. It's a minimization problem, but we're not going to go into minimization and differential calculus here. Okay, questions? Now this was kind of in a way of detraction from our major point here, and this was calculating thermodynamic properties. So you have to bear through a few more slides of formulas here. Now thermodynamically, of course, the pressure inside any system changes the thermodynamic properties. So we want to know how the change of the properties is going to affect parameters which you can measure and which are important. And if you have any liquid, what is important from practical viewpoint is what is the vapor pressure of the liquid. This tells you how fast the liquid is going to evaporate. So is water evaporating faster from inside droplets or from flat surfaces? What happens if you have droplets with different radius? What is the equilibrium pressure, vapor pressure of these droplets? Now, you have studied thermodynamics. You know that generally when you want to do some thermodynamic calculation, you do a process. So let's say we have bulk liquid, and we transform this bulk liquid into a droplet. The things that change is the pressure, the vapor pressure, which is in equilibrium with the bulk liquid or with the droplet, the Gibbs free energy outside and inside the droplet. So in order the droplet to be equilibrium, it has to have a vapor pressure outside of the liquid, right? This vapor pressure is for a flat surface, bulk, is the saturation vapor pressure. So every time I use this subscript set, this means that this is the case for flat interface without curvature. So what happens when we take this flat liquid and then we curve it and we create a droplet? Thermodynamically, of course, you know that the condition for equilibrium would be that the change in the Gibbs free energy of the vapor during the process would be equal to the change of the Gibbs free energy in the liquid during the process. Now the Gibbs free energy of vapor is expressed in this way. The change of Gibbs free energy is equal to kT times logarithm of the pressure minus kT times the logarithm of the pressure in the beginning of the process. So this gives you the change in Gibbs free energy in the vapor phase to keep the system in equilibrium. Now the change in the liquid has to be done. We have a change in the pressure here, so we have to do again thermodynamically, we have to do an integration of this term V times dP from the two pressures, from the original pressure of flat surface to the pressure of the curved surface. We already know that we can express the pressure in terms of 2 times gamma over 1 over R. So V times dP expressed in terms of the formula which we just discussed in the previous slide, which tells you that the pressure is 2 times gamma over R, leads to this integral here. And when we do the integration, we find out that the change in the Gibbs free energy inside the droplet is this one. The change of the Gibbs free energy outside the droplet is this one. And before I answer any concrete questions, when you equilibrate that, you have the formula. This is very important formula called Kelvin equation. You have a formula which relates the interfacial tension, Vm, which is volume per molecule of the liquid, which emerged here because of the integration, and the radius of the droplet, to the pressure outside the droplet related to the pressure of a flat surface times kT. Now this equation allows you to tell like that. Now I'm making a droplet and I change its radius. What is the vapor pressure of the gas outside the droplet, which keeps this droplet at equilibrium? And you can again calculate for droplets of different sizes. So if you take a droplet of radius 1 micrometer, the pressure in the droplet is going to be 1 point something atmosphere. The difference between the saturation pressure, the saturated pressure of free surface, and the droplet is going to be 1.001, so almost negligible. But then think about what happens if you decrease the size of the droplet to 10 nanometer. The pressure inside the droplets increases to 140 atmospheres, as we already had this example, and the equilibrium vapor pressure outside the droplet increases by almost 10%. Now, if you know thermodynamics, this is a lot. This tells you that the droplet, when you make it smaller, is no longer in equilibrium with the vapor pressure outside. And if it's not with equilibrium, if the vapor pressure of the equilibrium droplet is higher, what's going to happen with the droplet? Right. It's going to evaporate faster, or if it was originally in equilibrium, it's going to start evaporating. So that's why if you have a system of droplets, these droplets would evaporate easier than if you have a flat surface. They would evaporate easier because you have this capillary pressure inside the droplet. It wants to contract the droplet. So this contraction thermodynamically means that the droplet just wants to evaporate, it wants to get away from its state. Any questions about this procedure, about the thermodynamical aspects here and so on? Again, I know that this is fairly kind of just mathematical at this stage. We're going to discuss the colloidal applications of this in the next lecture, but we have to go through these fundamentals. Again, it's important to understand what the different parameters here mean. P is the pressure at equilibrium of the droplet. P sat is the pressure when you have flat surface in equilibrium with its vapors. The reason why the pressure outside the droplet in equilibrium would be higher than the saturation is because the droplet has higher pressure, capillary pressure, which wants to contract it. In a way, wants to evaporate it away. And Now, for the sake of the homeworks that you have to do, now you have this parameter K here. Now you have this parameter Vm, which is molecular volume. Now, when do we have K and when do we have R? What is the relation between K and R? Right. But when do you use K? Now you have two parameters, K and R. Now if you open different colloids books, you're going to find in some books you're going to find K, in other books you're going to find R. So you can see this equation written also in terms of R times T and so on, and you have some specific volume here. Now when do you use K, when do you use R? What is the difference between the two?
Per molecule, per mole.
Right. So kind of if you see a parameter K anywhere, that means that you're working per molecule. If you see parameter R, this means that you're working per mole. So for example, in this formula here, when you decide what parameter you should look in the books, if you have K in front of here, you should look volume per molecule, per single molecule. If you have to, if you're going to use R here, you're going to look for the molar volume. This is a very, I would make mistakes with just not using the appropriate parameter. This is a very easy source of just numerical errors. So just pay attention to that. This is important. And then now we know what happens when we have droplets and then bubbles. They would like to evaporate. Now what happens when we have solid particles? I'm going to specifically address the issues of solid particles a little bit late in the lecture. But what I want to tell you is that the same formula can be specified also for small solid nanoparticles. So now in this case, of course, a solid in solution in water is not equilibrium with its vapor, it's equilibrium with its dissolved molecular equivalent. So in this case, we have the equilibrium saturation concentration here, and this is the solubility. So what this formula tells you is that the solubility of small particles is higher when the particles are smaller. So you see when you increase the radius, the solubility here is going to decrease. When you decrease the radius, the solubility is going to increase. Now, which tells you that, imagine that, okay, let's think a little bit more practical here. You're formulating a medical product and you want the product to dissolve well in water, and it doesn't dissolve that much. Now, would you like to make the particles of the product smaller or larger? Right. This is one of the reasons, let's say, nanoparticles are these days considered for applications in different pharmaceutical products. The smaller you make them, the higher their solubility. So if you apply your product as nanoparticles, they're going to have higher effect on just because they dissolve better. But you have to be careful about that, because let's say Brian here is making metallic nanoparticles. Now they would like to dissolve, but they have very low solubility. So again, it's kind of like, not everything is important in this case. Now, this was an animation when I made it, but unfortunately this computer wouldn't play this as animation. So it describes one very important phenomenon which happens because as a consequence of what we studied here right now. And this phenomenon is called Oswald ripening. Now imagine you start with suspension of the same droplets or bubbles or soluble particles. Now if one of the particles is a little bit smaller than the other one, what is going to happen is that the solubility of this particle is going to be higher than this one. And what happens in reality is that the smaller particles dissolve and condense on the larger particles. This also happens with water vapors. If you have very small water droplets in air, you know that fog is a very unstable system. What happens is that the smaller droplets start evaporating and then condense on the larger droplets. The smaller the droplet, the higher the capillary pressure inside the droplet, which means that it's going to evaporate even faster. So once you start along this path, the final thermodynamically stable system would be eventually a very large system. So if you think about that, any dispersed system, any emulsion, foam, suspension, and so on, thermodynamically, it's not at equilibrium. At equilibrium state would be like, if it just becomes one large chunk of material. We're lucky that this does not happen, so we could do our profession. And the reason this does not happen is because in many cases these processes take place very slowly. In many cases they take place very fast. You can take water droplets in air and they very fast eventually recondense into larger droplets. It's a problem with emulsions. Eventually, when people make emulsion with very small droplets, the small droplets disappear just because they dissolve and then condense on the larger droplets. So this is also ripening. Now, I have saved you some thermodynamics formula here. You can find the relation between the evaporation, the evaporation energy and the Gibbs potential, the so-called Clausius equation. Substitute in the other formula and derive these two formulas, which are called in general Thomson equation, which tells you the effect on the capillary pressure on the radius on the temperature of evaporation of a droplet. It also, you can have this formula which relates the temperature of bubble formation in liquid to the capillary pressure in the droplet again. You can see that the smaller bubble you want to make, the higher temperature you need to create inside the liquid in order to make this small bubble. And the practical application of this, it's not exactly an application actually. Now you have seen the phenomenon of when you start heating up a bowl of water. Eventually the bubbles start bursting out, right? And if you measure the temperature is not going to be 100 degrees Celsius. It's going to be higher. And the reason for that is that in order to make the water boil, you have to make these small bubbles. In order to make these small bubbles, you have to overcome the capillary pressure because of the interfacial tension. And in order to do that, you have to increase the temperature. So thermodynamically, you have to apply more energy in order to make these small bubbles. So that's the reason why liquid either can boil violently, or why people put so-called boiling stones in water in order to avoid boiling. The boiling stones generate the small bubbles and allow them to grow instead of having to overcome this temperature kind of barrier. I'm seeing already some tiredness here, so any questions, comments, discussion here? Again, this is purely thermodynamic, but it has important practical consequences for a variety of systems. Let me go very briefly through this. Again, following on the thermodynamic path, you can calculate the energy of formation of a new phase. So in this case, you start with gas and you condense this gas into a liquid, for example. The Gibbs free energy that you need to do that is equal to the Gibbs free energy of the liquid minus the Gibbs free energy of the vapor times the volume, the number of molecules inside the droplet, plus the interfacial energy. If you express this is the volume, This is the Gibbs free energy of the droplet, and this is the interfacial energy. And you can see that actually they act against each other. So you may be in a condition where you have super saturated vapor, for example. The water would like to start condensing. However, in order to make small droplets, you need to overcome the interfacial tension barrier, which is energetically unfavorable. So that's why you have super saturated vapor, super cooled liquid in many cases, and so on. If you calculate how the overall dependence, how the overall Gibbs free energy is going to depend on the radius of the nucleus, of the droplet that you form, you are going to find out something like that. So eventually, you have to, if you form, let's say you form a nucleus of this size. Now you know you have an energy curve here. So this is very much as if you have a ball rolling on top of that curve. If you put the ball here, it's going to roll in this direction, right? So what is going to happen if you just occasionally nucleate a nucleus of this size? This nucleus, instead of growing, is going to decrease and disappear. And this is very important again in nucleation, new phases, formation of nanoparticles eventually. You have to be beyond a certain radius in order for the nucleus that you have formed spontaneously to grow. It's a big problem, for example, in protein crystallization. You can just have 2 or 3 or 4 eventually even protein molecules forming a new protein crystal, because they are so small that they're going to go back together in solution. So for protein crystallization, you have to have this many protein molecules getting together to form the nucleus of the protein crystal, and this doesn't happen that often. So, I mean, I have been doing protein crystallization as a postdoc, and if you do only protein crystallization, is there anybody here who does protein crystallization or something like that? This is a favorite job of biochemistry people. But eventually you have to wait for days or weeks for the protein crystal to start growing. Just because the nucleation process is rare enough, so it's not easy. And again, the thermodynamics of the surfaces explains why this has to be done. You only have growth only after you are beyond a certain radius of the nuclei. If you occasionally form something which is bigger than this, it's going to go this direction, spontaneously increase its radius by condensing more molecules. If you have something that's here, however, this nuclei is not going to survive thermodynamically, it's unstable, so it's going to dissolve. And this was the rest of the large formulas for today. In the remaining minutes, I'd like to go and discuss the aspects of surface, solid surfaces and so on. Now, before I do that, however, any questions here? Nucleation, droplets, particles, evaporation, condensation, stability. Daniel.
I've never thought of the evaporation increasing because of the size of the droplet before. I mean, surface. I thought of surface area a lot. And if you look at the Fick's equation for mass transport, which part of that is it? The transfer coefficient is where the solubility is taken into account,
right?
Or which is?
Yeah, this is a good question, and it relates to. Now you make let's say you want to have something which evaporates faster. Now you start eventually making it into smaller particles. Now, are you making this because you increase the surface area so it evaporates easier, or are you making this because the radius is going to make it shrink and evaporate? Typically, it depends on the size. Now, if you do the calculations here, you're going to find that these effects are important in the nanometer region. So, if you're thinking something that's on the scale of 1 nanometer, 10 nanometer, 100 nanometer or so, this something is going to have very significantly changed chemical potential, and it's going to have higher evaporation rate, it's going to have higher vapor pressure, and so on, just because it's so small. Now, when you just disperse particles in the micrometer range, you don't really expect that the thermodynamics is going to be so important. I mean, they're still too large. The pressure is not that high. If you remember, for water droplet, 1 micrometer water droplet has 1 atmosphere, which is significant but not that important. So if you disperse water droplets in 1 micrometer, these droplets would like to evaporate just kinetically. They have higher area, so they evaporate faster. If you disperse water droplets in 10 nanometers, these water droplets are going to evaporate immediately, not so much because of the large surface area, but because they are thermodynamically unstable. Or even if they don't evaporate, if they don't have where to evaporate, they are going to immediately change their size. The small droplets are going to become smaller, the large droplets are going to become larger, and you're going to have as a result rain. Right? Just only the large droplets survive. But it's a good point that you have to keep in mind that you may have to disperse a system just to increase its interfacial area in terms of kinetics of mass transfer. Or you want to disperse it very finely and then use the thermodynamic aspects because the solubility has increased so much. Okay. Just a few things about solids. Now you know what is adhesion and you know the effects of adhesion. Now if I want to take off this sheet of paper, it has some sticky substance here, I have to pull it off. And I have to pull it off against the force or energy of adhesion. This is a general picture of Izraelashvili which explains what adhesion is. You have, let's say, 2 solid surfaces, you pull them apart. Now you may have heard this word cohesion. Now cohesion is adhesion between similar surfaces. So you have 2 metallic blocks of the same metal and you pull them apart. This is cohesion. If you have metal and plastic and you want to pull them apart, this is adhesion. Eventually you may have to do this in third fluid, in water for example, or even air can be considered in third fluid. Eventually you may have a variety of other applications. What I'm going to go here is define somewhat thermodynamically the different stages of similar processes. Now first of all, cohesion. Now this is the case of solid bodies, this is the case of liquids. How does the work that you perform in order to pull 2 solids apart relates to the interfacial tension? Now eventually I define the interfacial tension as work that you need to create a unit area, right? But in the case of cohesion, when you pull a single body into 2 bodies, you create 2 interfacial areas. So the work that you have done actually, only 1/2 of the work that you have done goes for creating this surface, and the other one goes to the other surface. Similarly for liquids, if you want to make a new surface, you just need to kind of split the liquid in 1/2 area. And then when you open this area, it's going to make a 1 unit area. So the bottom line is that if you want to pull solid surfaces apart, or if you want to create a new liquid area, the interfacial tension is equal to 1/2 of the work that you need to do in order to pull them apart. Just because you're creating 2 times the area when you pull 2 things apart by cohesion. Similarly, you can think about what happens for surface energy and work of adhesion in third media. Now, you have 2 metallic blocks, for example, in water. You want to pull this metallic blocks apart. Now, thermodynamically, what you can think of this process is, first, you create a vacuum between the blocks, and then you fill this vacuum with the liquid between them. Or for the case of 2 liquids, if you want to create new area, you kind of split them like with a vacuum, like put in a vacuum edge in the middle, and then stretch this one out, and you create a unit area. Now, if you make the balance here, now the interfacial tension which you have created here, the new area that you have created, Now the work that you need to do is you have two surfaces of 1/2 area which you pull apart to create a unit area. Now the work that you need to do is equal to the work that you do for separating the two surfaces. Eventually, so first you make a work for like pulling the surfaces apart. You create work by then pushing liquid inside between the two surfaces. And finally, however, you need to lose some work in order to kind of like put the liquids between them. So if you just do the balance, it tells you that you have created a unit area. The interfacial tension that you have made is equal to 1/2 of the work of pulling two similar surfaces apart, plus 1/2 of the work of pulling the two similar surfaces of the media apart, minus the full work of introducing the newly created surface to the media, which is kind of abstract. I mean, like, what is this work? I mean, you don't exactly know how this work works, what is the work of creating a unit area, and so on. However, if you take the formula from the previous slide, which tells you what is the relation between the interfacial tension of a pure substance and the work that you need to create a unit area, then when you combine these two together, you have what is called Dupre equation. And that's important in colloidal science because it relates the interfacial tension between two liquids, for example, to the interfacial tension of the pure liquids and the work which you need to do in order to bring these two liquids together. And thermodynamically, it's very convenient for many cases. Because you can mix liquids, for example, you can measure the energy which is released by mixing of the liquids. And then you can relate this immediately to all the interfacial tensions in the system. Now, why do you want to know the interfacial tension of a certain system? Why I came to this question when we discuss solid surfaces, kind of practically. Let me give you an example here. Why you bother with this equation at all? Now, imagine you want to you have a solid surface and a liquid, and you want to understand everything in the system. Now, what you can do is you can put the liquid in contact with the solid surface, measure the energy, and then you know some of the parameters, and you can calculate all the other parameters, all the interfacial tensions in the system. Now, what is the really valuable thing that you can calculate out of this? The thing that you can't calculate that easily, measure that easily. Out of those parameters. Now imagine that you are discussing here a system which is solid and liquid. So you have the interfacial tension between the solid and the liquid, the interfacial tension of the solid, the interfacial tension of the liquid, and the work which we do in order to bring the solid and the liquid together to make the contact. Now, which is the really precious parameter which is difficult to measure experimentally?
Solid interfacial tension.
Right. How do you measure solid interfacial tension? For liquids, you can stretch the liquid, right? You can measure work by measuring let's say, release of temperature. But how do you measure the interfacial tension of a solid? If you try to pull apart a solid, you are acting against different plastic deformations and so on, so you cannot do that. So that's why people kind of come to this equation when you have solid surfaces, because this equation allows us to know the energy of a solid surface. And this energy of the solid surface is very important, and that's what we're going to discuss in the next lecture, because then when you put liquid on a solid surface, depending on the energy of the solid surface, you are going to have spreading, you're going to have contact angle, you're going to know how the liquid is going to wet the solid. So the way you understand three-phase contact angles, wetting, capillarity, liquid rise, some of the methods of measuring of interfacial tension and so on, all of those requires to know some energy of the solid surface. And that's what we're going to discuss next time. But right now, let's wrap up this lecture. This is just a reminder. We have gone through many things. Thank you for your attention, of course. I know that going through all these formulas without practical applications is a bit tiring. And we're going to change this starting from the next lecture. But what we have done here is we have gone through the two definitions of interfacial tensions, force and energy. And you know that they're equivalent. We have exactly the same dimensions between the two. We then went to calculate what is the pressure inside curved liquid interfaces. For the general case, we need to know the two radii of curvature. But for the case of droplets, bubbles, or similar radial spherical systems, you just have the pressure being equal to 2 times the interfacial tension divided by the radius. Now, there are different consequences of the curvature. We discussed the Kelvin equation, the vapor pressure outside the liquid phase. There is the Oswald tripening, which tries to destabilize any suspension, tries to make the small droplet smaller and the large droplet larger. There is the nucleation energy barrier, which can be important in many practical processes. And finally, we know how to relate the surface energy and the work that we do in order to bring surfaces together, which is important for solid surfaces. So now we have all the apparatus that we need to have in order to discuss next time different types of capillary phenomena, wetting, capillary rise, capillary forces, and so on. So that's the final slide. We have 1 minute for questions, and of course we can continue with questions afterwards. Thanks for our distantification students too. Any questions? Okay, then I should assume that you have followed through everything that I have shown here. Thanks.